Imagine this. You're in a car, steadily accelerating. You look around, but there's no gas pedal, no engine, nothing you can see that's pushing you forward. That's the universe we live in. Everything is moving apart, faster and faster, and we don't know why. This is the mystery of dark energy, a force so powerful it's pulling the very fabric of space apart. It's a cosmic conundrum that's been baffling scientists for decades. Why is the universe accelerating? What is this dark energy, and how is it shaping our cosmic destiny? Stick around, because we're about to dive into one of the greatest paradoxes of our time, the expanding universe. The universe is expanding, and it's not just stretching out like a balloon, it's accelerating. This acceleration is one of the most baffling discoveries in cosmology. When astronomers first observed distant supernovae in the late 20th century, they expected to see the expansion of the universe slowing down due to gravity. Instead, they found that the expansion was speeding up. This acceleration implies that something is counteracting gravity, pushing the universe apart. That something is what scientists have dubbed dark energy. Dark energy is a mysterious force that makes up about 68% of the universe's total energy density. It's called dark because it doesn't interact with light, making it invisible and difficult to detect. The exact nature of dark energy remains one of the biggest unsolved problems in physics. One popular theory suggests that dark energy is a property of space itself, a kind of energy associated with the vacuum of space. This idea is often referred to as the cosmological constant, a concept first introduced by Albert Einstein. However, the observed value of dark energy is incredibly small compared to what quantum theory predicts, leading to what's known as the cosmological constant problem. The accelerating universe presents a paradox. Why is the universe expanding faster and faster when gravity should be pulling it together? This paradox challenges our understanding of the fundamental forces of nature. One possible explanation is that dark energy is a dynamic quantity, changing over time. If dark energy evolves, it could explain the observed acceleration. Another intriguing possibility is that our universe is part of a larger multiverse, and the acceleration is due to interactions with other universes. These ideas are speculative, but they highlight the depth of the mystery surrounding dark energy. The implications of an accelerating universe are profound. If the expansion continues to speed up, the universe could end in a big freeze, where galaxies become isolated islands in an ever-expanding void. This scenario raises questions about the ultimate fate of the universe and the possibility of life in the distant future. Understanding dark energy is not just an academic exercise. It's a quest to uncover the fundamental nature of reality. The mystery of dark energy provokes curiosity and drives scientists to push the boundaries of knowledge, exploring the deepest questions about the cosmos. Early observations. The universe, in its vast expanse, has always been a subject of fascination and intrigue. Early observations of its behavior have led to groundbreaking discoveries, particularly the realization that the universe is not just expanding, but accelerating in its expansion. This acceleration is attributed to a mysterious force known as dark energy, which constitutes about 68% of the universe's total energy density. The first hints of this phenomenon came from studying distant supernovae, which appeared fainter than expected. This faintness suggested that the universe's expansion was speeding up, defying the gravitational pull that should have been slowing it down. One of the most puzzling aspects of these early observations is the cosmic coincidence problem. This paradox questions why the density of dark energy is comparable to the density of matter at this particular epoch in the universe's history. Given the vast differences in their scales and behaviors, this coincidence is perplexing. It's like finding a single grain of sand on a beach that somehow matches the exact color and texture of a specific pebble miles away. This observation provokes curiosity about the underlying mechanisms driving the universe's acceleration and the nature of dark energy itself. The acceleration of the universe also raises questions about its ultimate fate. If the expansion continues to accelerate, the universe could end in a big freeze, where galaxies drift apart, stars burn out, and the universe becomes increasingly cold and empty. Alternatively, if dark energy's behavior changes, the outcome could be vastly different. These scenarios highlight the importance of understanding dark energy, as it holds the key to predicting the universe's long-term evolution. Early observations have set the stage for ongoing research, driving scientists to explore the cosmos with ever greater precision and ingenuity. Hubble's law. In the vast expanse of the cosmos, galaxies aren't just drifting aimlessly. They're fleeing from each other at an ever-increasing pace. This phenomenon, known as the accelerating universe, is one of the most perplexing discoveries in modern cosmology. At the heart of this mystery lies Hubble's law, a simple yet profound relationship that connects the distance of galaxies to their speed. Edwin Hubble, the astronomer after whom the law is named, observed that the farther a galaxy is from us, the faster it's moving away. This isn't due to some galactic game of keep away, but rather a stretching of space itself, a consequence of the Big Bang's aftermath. Now, here's where things get intriguing. If the universe is expanding, why is it speeding up? This is where dark energy comes into play. Picture a rubber band stretching. Initially, it requires effort to pull it apart, but as it stretches, it becomes easier. However, in our universe, the opposite is happening. The expansion is not slowing down due to gravity, as one might expect, but accelerating. This counterintuitive behavior suggests the presence of a mysterious force, dark energy, which makes up about 68% of the universe's energy density. It's as if the universe is filled with an invisible, repulsive force that's pushing galaxies apart at an increasing rate. The paradox here is that we don't understand what dark energy is. It doesn't emit light or absorb it, making it invisible to our telescopes. Yet, its effects are undeniable. One way to grasp this is to think of the universe as a loaf of raisin bread baking in the oven. As the bread rises, the raisins, representing galaxies, move farther apart. But in our universe, the bread isn't just rising. It's rising faster and faster, and we're not entirely sure why. This acceleration is a cosmic puzzle that challenges our understanding of physics. It's a reminder that the universe is full of surprises, and there's still so much we don't know. The cosmological principle. The universe, on scales much larger than the size of galaxy clusters, appears to be the same in all directions and at every point in space. This observation is the foundation of the cosmological principle, a fundamental assumption in modern cosmology. It suggests that the universe is homogeneous and isotropic, meaning its properties are uniform and look the same from any location. This principle is crucial for understanding the large-scale structure and behavior of the universe. It allows scientists to apply the same physical laws and models everywhere, simplifying the complex task of studying the cosmos. However, the cosmological principle leads to intriguing paradoxes and questions. For instance, if the universe is truly uniform, why do we observe structures like galaxies and galaxy clusters? These formations seem to contradict the idea of homogeneity. The answer lies in the concept of scale. On very large scales, the distribution of matter does indeed even out, and the universe appears uniform. But on smaller scales, gravity causes matter to clump together, forming the structures we observe. This duality is a fascinating aspect of the cosmological principle, highlighting the complexity of the universe. Another paradox arises when considering the acceleration of the universe's expansion. Observations of distant supernovae have shown that the universe is expanding at an accelerating rate. This acceleration is attributed to dark energy, a mysterious force that counteracts gravity. The cosmological principle implies that dark energy is uniformly distributed throughout the universe. Yet, its nature and origin remain unknown, provoking curiosity and driving extensive research. Understanding dark energy is key to unraveling the ultimate fate of the universe. The cosmological principle also raises questions about the universe's geometry. If the universe is isotropic and homogeneous, its shape must be one of three possibilities: flat, spherical, or hyperbolic. Each of these geometries has different implications for the universe's fate. A flat universe would expand forever, a spherical universe would eventually collapse, and a hyperbolic universe would expand at an accelerating rate. Current observations suggest that the universe is very close to being flat, but the precise nature of its geometry remains an active area of study. This ongoing research not only deepens our understanding of the cosmological principle, but also sheds light on the fundamental nature of the universe. The Standard Model of Cosmology. The Standard Model of Cosmology is a framework that helps us understand the universe's origin, evolution, and ultimate fate. It's built on several key observations and theories, including the Big Bang, the cosmic microwave background radiation, and the large-scale structure of the universe. This model has been remarkably successful in explaining a wide range of phenomena, from the abundance of light elements to the distribution of galaxies. However, it also presents some intriguing paradoxes and unanswered questions, particularly when it comes to the accelerating expansion of the universe. One of the most significant pieces of evidence for the accelerating universe comes from observations of type I supernovae. These supernovae serve as standard candles for astronomers, allowing them to measure distances in the universe. In the late 1990s, two independent teams of astronomers found that distant type I supernovae were dimmer than expected, suggesting that the expansion of the universe is accelerating. This acceleration is attributed to a mysterious component called dark energy, which makes up about 68% of the universe's total energy density. The nature of dark energy remains one of the biggest mysteries in cosmology. The Standard Model of Cosmology incorporates dark energy through a term in Einstein's field equations known as the cosmological constant. This constant represents a uniform energy density pervading space, which can drive the accelerated expansion of the universe. However, the value of the cosmological constant predicted by quantum field theory is vastly larger than the observed value, a discrepancy known as the cosmological constant problem. This paradox highlights the limitations of our current understanding and the need for new physics to explain dark energy. Another paradox arises from the fine-tuning required for the universe to have the properties it does. The energy density of dark energy is incredibly fine-tuned to be just a few orders of magnitude smaller than the energy density of matter in the universe today. If it were much larger, the universe would have expanded too rapidly for galaxies and stars to form. This fine-tuning suggests that there might be a deeper underlying principle or mechanism at work, perhaps related to the multiverse or anthropic selection effects. These paradoxes and mysteries make the study of dark energy and the accelerating universe one of the most exciting and active areas of research in cosmology. Dark energy, a necessary concept. In the grand cosmic ballet, galaxies are not just twirling gracefully. They're being flung outward at an ever-increasing pace. This acceleration is not some cosmic whim, but a consequence of a mysterious force or energy that permeates the universe. Enter dark energy, a concept that has become necessary to explain this perplexing observation. It's a bit like discovering that your car is speeding up when you're not pressing the accelerator. You'd be scratching your head, right? That's precisely the situation astronomers found themselves in when they observed the universe's expansion rate. Dark energy is estimated to make up about 68% of the universe's total energy density. It's a staggering figure, especially when you consider that everything we can see, from the smallest atom to the largest galaxy, accounts for just 5% of the universe's energy density. The rest is dark matter, another enigmatic component that doesn't emit, absorb, or reflect light. But unlike dark matter, which exerts a gravitational pull, dark energy seems to have a repulsive effect, driving the acceleration of the universe's expansion. It's a cosmic push that's counterintuitive, given our everyday experiences with gravity. The concept of dark energy was first proposed to explain why the universe's expansion is accelerating, a discovery that earned the 2011 Nobel Prize in Physics. But it's not without its paradoxes. For instance, if dark energy is a property of space itself, as proposed by Albert Einstein's cosmological constant, then its density should remain constant as space expands. However, if dark energy is a dynamic field, its density could change over time, leading to different scenarios for the universe's fate. This is where things get really interesting. If dark energy's density increases, it could eventually tear apart all structures in the universe, a scenario aptly named the Big Rip. On the other hand, if its density decreases, the universe might expand forever, but at a slower pace. The uncertainty is what makes this topic so intriguing. It's like trying to predict the weather without knowing if it's going to rain cats and dogs or stay sunny. The possibilities are vast, and the implications are profound. Einstein's cosmological constant. In the vast expanse of the cosmos, galaxies are not just drifting apart, they're accelerating away from each other. This acceleration is one of the most profound mysteries of modern cosmology. Enter Einstein's cosmological constant, a term he initially introduced to his field equations to allow for a static universe. It's a measure of the energy density of space itself, a kind of inherent stiffness or resistance to change. This constant, denoted by the Greek letter lambda, represents a form of energy that permeates all of space and exerts a repulsive force, counteracting gravity. It's as if space has a built-in springiness, pushing things apart. The cosmological constant is incredibly small, yet its effects are profound. It's like a tiny, persistent nudge that, over billions of years, leads to the accelerating expansion of the universe. This energy is often referred to as dark energy, and it makes up about 68% of the total energy density of the universe. The rest is a mix of dark matter and ordinary matter. The paradox here is that while we can measure the effects of dark energy, we don't yet understand its fundamental nature. It's a bit like knowing the symptoms of a disease, but not the cause. One of the most intriguing aspects of the cosmological constant is its fine-tuned value. If it were even slightly larger, the universe would have expanded too rapidly for galaxies to form. If it were smaller, the universe might have collapsed in on itself long ago. This fine-tuning suggests that there might be some deeper principle at work, something we haven't yet discovered. It's a tantalizing clue, a hint that there's more to the story than we currently understand. The cosmological constant, once a footnote in Einstein's equations, now sits at the heart of some of the biggest questions in cosmology. The accelerating universe. In the grand cosmic ballet, galaxies are not just drifting aimlessly. They're being pushed apart at an ever-increasing rate. This acceleration is one of the most perplexing discoveries in modern cosmology, defying our intuitive understanding of gravity's pull. When we observe distant supernovae, we expect to see them slowing down due to the gravitational tug of the universe's mass. Instead, we find they're speeding up, as if some unseen force is overriding gravity's brakes. This phenomenon, known as the accelerating universe, has sent scientists scrambling for explanations. One leading candidate for this cosmic acceleration is dark energy, a mysterious force that makes up about 68% of the universe's energy density. It's called dark because it doesn't interact with light, making it invisible to telescopes. Yet, its gravitational effects are undeniable. Think of it like an invisible wind, pushing galaxies apart. The more the universe expands, the more this wind seems to strengthen, creating a paradox. The faster the universe expands, the more dark energy there is to drive that expansion. It's a self-reinforcing cycle that challenges our understanding of the cosmos. The accelerating universe also raises profound questions about the ultimate fate of the cosmos. If this trend continues, galaxies will eventually become so distant that they'll be forever beyond our observational horizon. The night sky will grow darker, and the universe will become increasingly isolated. This scenario, known as the Big Freeze or heat death, is one possible endgame for our universe. Yet, the nature of dark energy remains so enigmatic that other outcomes can't be ruled out. Perhaps dark energy will decay, or maybe it's a sign of a deeper, more complex theory of gravity waiting to be discovered. The paradoxes abound, and with them, the tantalizing promise of new physics. Supernovae observations. In the grand cosmic ballet, supernovae are the dramatic, explosive finales of certain stars' lives. These stellar explosions are incredibly bright, briefly outshining entire galaxies. Astronomers have long used them as standard candles to measure distances in the universe. But in the late 20th century, something peculiar emerged from these observations. Distant supernovae weren't quite as bright as expected. This wasn't a mere observational error. It hinted at something profound. The universe wasn't just expanding, it was accelerating. This acceleration suggested the presence of an unknown force, now called dark energy, pushing the universe apart. The paradox here is striking. Gravity, the force that pulls everything together, should be slowing down the expansion of the universe. Yet, the universe is expanding faster and faster. Supernovae observations, particularly type I supernovae, are crucial because they provide a consistent baseline for comparison. These supernovae occur when a white dwarf star accumulates too much mass from a companion star, reaching a critical point and exploding. Because the initial mass of the white dwarf is always around the same, these supernovae have a predictable brightness. By comparing the observed brightness of distant supernovae to their expected brightness, astronomers can infer their distances. The results showed that the farthest supernovae were dimmer than expected, indicating they were farther away than predicted by a decelerating universe. This acceleration poses a challenge to our understanding of the cosmos. Dark energy, which makes up about 68% of the universe's energy density, is the leading explanation. But what is dark energy? Is it a property of space itself, as Einstein's cosmological constant suggests, or something more exotic? The mystery deepens when considering that dark energy's density doesn't dilute as the universe expands, unlike matter and radiation. This constant density means its influence grows stronger over time, further accelerating the universe's expansion. The paradox of an accelerating universe, revealed through supernovae observations, has reshaped our understanding of cosmology and propelled us into a new era of astrophysical inquiry. It's a reminder that the universe is full of surprises, and our quest to understand it is far from over. Evidence for dark energy. In the grand cosmic ballet, galaxies are not just twirling gracefully. They're being propelled by an unseen force, a mysterious entity we've dubbed dark energy. This enigmatic power is causing the universe to expand at an accelerating rate, a phenomenon that was first hinted at in the late 20th century. The evidence for dark energy is as compelling as it is baffling, rooted in observations that challenge our understanding of the cosmos. One of the most persuasive pieces of evidence comes from studying distant supernovae. These stellar explosions act as cosmic lighthouses, their brightness allowing astronomers to measure vast distances. In the 1990s, two independent teams of astronomers were using these supernovae to chart the universe's expansion history. To their surprise, they found that the light from these distant explosions was fainter than expected, suggesting that the expansion of the universe was not slowing down due to gravity, as one might anticipate, but speeding up. This acceleration implied the existence of a repulsive force, which we now call dark energy. The cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, also provides compelling evidence. This ancient light has been traveling through space for nearly 13.8 billion years, carrying with it a wealth of information about the universe's early days. By studying the CMB, scientists can infer the universe's composition and geometry. The data reveals that the universe is geometrically flat, a condition that can only be achieved if the universe is filled with a certain amount of dark energy. This finding aligns with the supernova observations, painting a consistent picture of a universe dominated by dark energy. Yet, the nature of dark energy remains one of the most profound paradoxes in modern cosmology. It behaves unlike anything we've encountered before, exerting a repulsive force that counteracts gravity on cosmic scales. This paradox is not just a curiosity, it's a challenge to our fundamental understanding of physics. Dark energy makes up about 68% of the universe's total energy density, yet we have no idea what it is. This mystery provokes a sense of awe and curiosity, driving scientists to push the boundaries of our knowledge. The quest to understand dark energy is not just about unraveling the secrets of the cosmos. It's about redefining the very laws of nature, the composition of the universe. The universe is a vast and complex tapestry, woven with threads of matter and energy that we are still trying to fully understand. For decades, scientists believed that the expansion of the universe, initiated by the Big Bang, was gradually slowing down due to the gravitational pull of its constituent matter. However, observations of distant supernovae in the late 20th century revealed a startling truth. The universe's expansion is not slowing down, it's accelerating. This acceleration is attributed to a mysterious force known as dark energy, which makes up approximately 68% of the universe's total energy density. But what does this mean for the composition of the universe? Matter, both visible and dark, accounts for about 32% of the universe's energy density. Visible matter, the stuff we can see and interact with, stars, planets, galaxies, makes up a mere 5% of this. The remaining 27% is dark matter, a substance that does not emit, absorb, or reflect light, making it invisible to our current detection methods. Dark matter's presence is inferred through its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light around massive objects. Despite its elusive nature, dark matter plays a crucial role in the large-scale structure and dynamics of the universe. The remaining 68% of the universe's energy density is attributed to dark energy. Unlike matter, which exerts a gravitational pull, dark energy is thought to exert a repulsive force, driving the accelerated expansion of the universe. The exact nature of dark energy remains one of the most profound mysteries in cosmology. One leading hypothesis is that dark energy is a property of space itself, associated with the cosmological constant, a term introduced by Albert Einstein in his field equations of general relativity. According to this idea, as the universe expands, more space comes into existence, and with it, more dark energy, leading to an ever-accelerating expansion. The composition of the universe presents a paradox. While we can account for the behavior of visible matter and dark matter through gravitational interactions, dark energy defies our current understanding of fundamental forces. This paradox provokes curiosity and drives scientific inquiry. For instance, if dark energy is indeed a property of space, what implications does this have for the ultimate fate of the universe? Will the accelerated expansion lead to a big freeze, where galaxies become isolated islands in an ever-expanding void? Or are there other possibilities, such as the existence of a dynamic dark energy that changes over time? These questions highlight the need for continued exploration and innovation in cosmology as we strive to unravel the enigmatic fabric of the universe. Matter, and dark energy. In the vast expanse of the cosmos, the dance of matter, and dark energy orchestrates the universe's fate. Ordinary matter, the stuff we see and interact with daily, makes up a mere 5% of the universe's energy density. This includes atoms, molecules, and everything composed of protons, neutrons, and electrons. Stars, planets, and even our own bodies are all part of this tiny fraction. Yet, this matter is crucial for forming structures like galaxies and galaxy clusters, which we can observe and study. Dark matter, on the other hand, is an invisible entity that doesn't emit, absorb, or reflect light, making it undetectable by conventional means. Its presence is inferred through gravitational effects on visible matter, like the rotation of galaxies and the bending of light. Dark matter accounts for about 27% of the universe's energy density. It's a paradoxical substance that doesn't interact with light, but interacts gravitationally, shaping the large-scale structure of the universe. Without dark matter, galaxies would fly apart, and the universe would look vastly different. The most enigmatic component is dark energy, a mysterious force that permeates all of space and drives the acceleration of the universe's expansion. It constitutes roughly 68% of the universe's energy density. The discovery of dark energy's influence was a surprise, as it contradicted the expectation that the universe's expansion would slow down due to gravity. Instead, observations of distant supernovae revealed that the expansion is speeding up. This acceleration suggests that dark energy is a property of space itself, exerting a repulsive force that counteracts gravity. The nature of dark energy remains one of the most profound mysteries in cosmology, challenging our understanding of the universe's fundamental laws. The nature of dark energy. Dark energy is a mysterious and perplexing component of the universe that is believed to be responsible for its accelerating expansion. It makes up approximately 68% of the universe's total energy density, yet its nature remains one of the most significant unsolved problems in physics. The concept of dark energy was first proposed to explain observations that distant supernovae were dimmer than expected, suggesting that the universe's expansion is speeding up rather than slowing down due to gravity. This discovery was so unexpected that it led to the Nobel Prize in Physics in 2011. The term dark in dark energy doesn't refer to its color, but rather to the fact that it doesn't emit, absorb, or reflect light, making it invisible to telescopes. One of the most intriguing aspects of dark energy is its paradoxical behavior. According to Einstein's theory of general relativity, gravity should cause the expansion of the universe to slow down over time. However, observations of distant supernovae and the cosmic microwave background radiation indicate that the expansion is actually accelerating. This acceleration suggests the presence of a repulsive force counteracting gravity, which is what dark energy is thought to be. The nature of this force is still unknown, and it challenges our understanding of fundamental physics. Some theories suggest that dark energy is a property of space itself, while others propose that it is a new type of dynamic field. The paradox deepens when considering the density of dark energy. Measurements indicate that its density is incredibly low, yet it dominates the universe's energy budget. This is puzzling because, as the universe expands, the density of matter and radiation decreases, but the density of dark energy remains constant. This implies that dark energy's influence will only grow stronger over time, leading to a future where galaxies become increasingly isolated from one another. The exact mechanism behind this constant density is another mystery that scientists are eager to unravel. The study of dark energy is not just about understanding the past and present of the universe, but also about predicting its ultimate fate. The search for the nature of dark energy involves a variety of approaches, including theoretical models and observational astronomy. One prominent theoretical model is the cosmological constant, a term Einstein initially introduced into his field equations to allow for a static universe. When it was later found that the universe is expanding, Einstein abandoned the cosmological constant, calling it his biggest blunder. However, the discovery of dark energy has revived interest in this concept. The cosmological constant represents a form of energy inherent to space itself, exerting a repulsive force that counteracts gravity. If dark energy is indeed the cosmological constant, it suggests that the vacuum of space is not empty, but filled with a form of energy that drives the acceleration of the universe. Quintessence, a dynamic alternative. In the vast cosmic ballet, galaxies are not just dancing. They're hurtling away from each other at an ever-increasing pace. This acceleration is attributed to dark energy, a mysterious force that makes up about 68% of the universe's energy density. But what if dark energy isn't a constant, unchanging force? Enter quintessence, a dynamic alternative that could explain the universe's accelerating expansion. Quintessence is a hypothetical form of dark energy that changes over time and space. Unlike the cosmological constant, which is a static value, quintessence is a dynamic field that can evolve. This evolution could lead to different behaviors of dark energy in the past, present, and future. For instance, it might have been repulsive in the past, driving the acceleration we see today, but could become attractive in the future, potentially leading to a big crunch instead of a big freeze. One of the most intriguing aspects of quintessence is its potential to explain the coincidence problem. This paradox questions why dark energy is only now becoming dominant, when the universe is so much older than its current expansion phase. If dark energy were a constant, its density would have been much higher in the past, overwhelming the effects of gravity and preventing structures like galaxies from forming. Quintessence, however, can change over time, offering a possible solution to this conundrum. Moreover, quintessence could also address the fine-tuning problem. The density of dark energy is incredibly fine-tuned to its current value, allowing for the formation of structures like galaxies and stars. If it were even slightly different, the universe might have expanded too quickly or too slowly, making life as we know it impossible. Quintessence's dynamic nature could provide a natural explanation for this fine-tuning, as its value could have evolved to its current state over time. This field is still theoretical, but it opens up fascinating possibilities for understanding the universe's acceleration. The equation of state. In the vast expanse of the cosmos, a mysterious force known as dark energy is causing the universe to expand at an accelerating rate. To understand this phenomenon, scientists often turn to the equation of state, a fundamental concept in cosmology that relates the pressure of a substance to its energy density. For dark energy, this equation is typically denoted as W equals P/ρ superscript 2, where P is the pressure, ρ is the energy density, and c is the speed of light. The value of W is crucial in determining the nature of dark energy and its impact on the universe's expansion. The equation of state for dark energy has puzzled scientists for decades. Observations suggest that the value of W is approximately -1, which corresponds to a form of energy known as a cosmological constant. This value implies that dark energy has a negative pressure, which counteracts gravity and drives the accelerated expansion of the universe. However, the exact nature of dark energy remains one of the biggest mysteries in modern physics. Some theories propose that dark energy is a dynamic quantity, changing over time, which would mean that the equation of state is not constant. This introduces a paradox. If dark energy is dynamic, why do current observations suggest a value of West that is so close to -1? One of the most intriguing aspects of the equation of state is its role in the fate of the universe. If the value of W is greater than -1, the accelerated expansion will eventually tear the universe apart in a scenario known as the Big Rip. Conversely, if W is less than -1, the universe could collapse in a big crunch. A value of W exactly equal to -1 suggests a more stable future, but the exact implications are still unclear. This uncertainty provokes curiosity and drives researchers to develop new theories and conduct more precise observations. For instance, upcoming missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope aim to measure the equation of state with unprecedented accuracy, potentially shedding light on the nature of dark energy and the ultimate fate of the cosmos. The equation of state also plays a crucial role in understanding the distribution of matter in the universe. Dark energy's negative pressure affects the growth of cosmic structures, such as galaxies and galaxy clusters. By studying these structures, scientists can infer the properties of dark energy and refine their understanding of the equation of state. For example, the large-scale structure of the universe, as observed in galaxy surveys, provides valuable clues about the balance between dark energy and gravity. These observations often reveal paradoxes, such as the apparent discrepancy between the observed rate of structure growth and the predictions based on the cosmological constant. Resolving these paradoxes requires a deeper understanding of the equation of state and the underlying physics of dark energy, cosmic acceleration, and the fate of the universe. The universe, in its vast expanse, has been expanding since the Big Bang. For decades, scientists assumed this expansion was slowing down due to gravity. However, observations of distant supernovae in the late 20th century revealed a startling truth. The universe's expansion is not slowing down, it's accelerating. This phenomenon, known as cosmic acceleration, has profound implications for the fate of the universe. The driving force behind this acceleration is a mysterious entity called dark energy, which makes up about 68% of the universe's total energy density. Its nature remains one of the most significant unsolved problems in physics. The discovery of cosmic acceleration presents a paradox. Gravity, as understood through general relativity, should decelerate the expansion of the universe. Yet, the universe is expanding at an ever-increasing rate. This paradox has led scientists to propose various theories. One prominent explanation is that dark energy is a property of space itself, causing it to expand. This idea aligns with Einstein's cosmological constant, a term he initially introduced to his field equations to allow for a static universe but later abandoned. The cosmological constant represents a constant energy density filling space homogeneously. However, the value predicted by quantum field theory is vastly different from the observed value, leading to what is known as the cosmological constant problem. Another intriguing aspect of cosmic acceleration is its implications for the ultimate fate of the universe. If the acceleration continues indefinitely, the universe will end in a big freeze or heat death. In this scenario, galaxies will move away from each other at an ever-increasing rate, eventually becoming so distant that they will be invisible to each other. Stars will burn out, and the universe will become cold, dark, and devoid of life. This fate is often compared to the Big Rip, where the expansion becomes so rapid that it tears apart galaxies, stars, and even atoms. The exact nature of this end depends on the properties of dark energy, which remain uncertain. The study of cosmic acceleration and dark energy is ongoing. Scientists are using various methods to probe the nature of dark energy, including studying the cosmic microwave background, large-scale galaxy surveys, and the distribution of dark matter. Each method provides a different perspective on the universe's expansion and the role of dark energy. The mystery of dark energy challenges our understanding of fundamental physics and cosmology. It provokes curiosity and drives innovation in theoretical and observational astronomy. As we delve deeper into this enigma, we may uncover new principles that revolutionize our understanding of the universe. The Big Freeze scenario. Dark energy, a mysterious and pervasive force, is driving the universe to expand at an accelerating rate. This phenomenon, first observed through the study of distant supernovae, has led scientists to propose various scenarios about the ultimate fate of the cosmos. One of the most chilling possibilities is the Big Freeze scenario, a future where the universe becomes increasingly cold, empty, and desolate. At the heart of this scenario lies a paradox. If the universe is expanding faster and faster, what happens to the matter and energy within it? As galaxies drift apart, the space between them grows, and interactions become rarer. Stars will burn out, and new ones will cease to form. The cosmos will grow darker and colder, a stark contrast to the vibrant, dynamic universe we observe today. The Big Freeze scenario presents a counterintuitive twist. One might expect that an expanding universe would eventually slow down, but dark energy acts as a repulsive force, counteracting gravity. This leads to a future where the universe is not just expanding, but doing so at an ever-increasing rate. Over vast stretches of time, this acceleration will have profound consequences. Galaxies will become isolated islands, unable to interact or influence one another. The night sky, once filled with the light of countless stars, will grow increasingly barren. This raises a curious question. If the universe is destined to become a cold, empty place, why does it appear so full of life and activity now? The answer lies in the timescales involved. The processes that lead to the Big Freeze unfold over trillions of years, far beyond the current age of the universe. Another intriguing aspect of the Big Freeze scenario is the role of entropy. Entropy, a measure of disorder, tends to increase over time. In a universe dominated by dark energy, the increase in entropy is inevitable. Stars will burn out, and the energy they release will dissipate into the void. Eventually, even black holes will evaporate, leaving behind a universe filled with a thin soup of photons and particles at nearly absolute zero. This final state, often referred to as the heat death of the universe, is a paradox in itself. It suggests that the universe, despite its initial conditions of high energy and density, is fated to end in a state of maximum entropy and minimum energy. This raises philosophical questions about the nature of existence and the ultimate fate of all things. The Big Freeze scenario also challenges our understanding of time and causality. In a universe where galaxies are increasingly isolated, the concept of a shared past becomes meaningless. Each galaxy will evolve independently, leading to a multitude of possible futures. This raises the question, if the universe is destined to become a cold, empty place, does it matter what happens in the interim? The answer, perhaps, lies in the value we place on the present. The universe, as we know it, is a fleeting moment in the grand tapestry of time. It is a place of wonder, discovery, and possibility. The Big Freeze scenario reminds us to cherish the here and now, for it is all we have. The Big Rip scenario. Dark energy, a mysterious force permeating the universe, is causing the cosmos to expand at an accelerating rate. This phenomenon, first observed through the study of distant supernovae, has led scientists to propose various scenarios about the ultimate fate of the universe. One of the most intriguing and somewhat unsettling of these is the Big Rip scenario. In this model, the acceleration driven by dark energy doesn't just continue indefinitely, it escalates. The expansion becomes so rapid that it eventually tears apart all structures in the universe, from galaxies to planets, down to the very fabric of space-time itself. The idea is both fascinating and terrifying, a cosmic end that challenges our understanding of physics and existence. The Big Rip scenario hinges on the nature of dark energy, which is often described by the cosmological constant, a term in Einstein's field equations. If dark energy is indeed a constant, its density remains unchanged as the universe expands. This leads to a gentle, ongoing acceleration. However, if dark energy evolves over time, its density could increase, leading to a more dramatic expansion. In the Big Rip scenario, the density of dark energy grows without bound, causing the expansion rate to increase exponentially. This would result in a future where the fabric of space-time is stretched beyond recognition, ultimately ripping apart everything in its path. The paradox here is that while dark energy is invisible and its nature is unknown, its effects are undeniably real and observable. Consider the fate of a hypothetical planet in a universe undergoing a big rip. Initially, the planet's distance from its star increases slowly. Over billions of years, this distance grows exponentially, eventually causing the planet to drift into the cold, dark void of space. The star itself isn't safe. As the expansion accelerates, it too is torn apart, followed by the destruction of atoms and subatomic particles. The paradox lies in the fact that while the universe is expanding, the forces holding matter together are finite. The Big Rip suggests that even the strongest forces, like the nuclear force holding atomic nuclei together, can be overcome by the relentless expansion driven by dark energy. This challenges our understanding of the fundamental forces of nature and their limits. The Big Rip scenario also raises profound questions about the ultimate fate of information and the laws of physics. In a universe undergoing a Big Rip, all structures, including those that store information, are eventually destroyed. This poses a challenge to the idea of conservation of information, a principle that states information can never be truly lost. If the Big Rip erases all information, it would imply a fundamental breakdown of the laws of physics as we know them. Moreover, the scenario suggests that the universe has a finite lifespan, a concept that contrasts with the idea of an eternal, unchanging cosmos. The Big Rip scenario, with its dramatic and catastrophic end, provokes curiosity and forces us to confront the limits of our knowledge and the mysteries that still lie ahead. The Big Crunch scenario. The universe is expanding at an accelerating rate, a discovery that has baffled scientists and led to the concept of dark energy. This mysterious force, which makes up about 68% of the universe, is driving this acceleration. But what if the universe didn't expand forever? What if it contracted? This brings us to the Big Crunch scenario, a theoretical end to the universe where it collapses back into a hot, dense state, much like the conditions after the Big Bang. In the Big Crunch scenario, gravity overcomes the outward force of dark energy, halting the expansion of the universe and pulling everything back together. This idea is based on the assumption that the density of the universe is high enough for gravity to reverse the expansion. However, current observations suggest that the universe's expansion is accelerating, not slowing down. This presents a paradox. If dark energy is causing the universe to expand faster, how can the Big Crunch scenario even be possible? One way to reconcile this is to consider that dark energy might not be constant. Perhaps it changes over time, or perhaps it's not the only force at play. Some theories suggest that dark energy could become repulsive in the future, pushing the universe apart even faster. Others propose that the universe might be shaped in a way that allows for a big crunch, despite the current acceleration. These ideas are speculative, but they highlight the complexity of the universe and the many mysteries that remain unsolved. The Big Crunch scenario also raises intriguing questions about the fate of information and entropy. In a universe that contracts, would entropy decrease, violating the second law of thermodynamics? Would information be lost or preserved? These paradoxes challenge our understanding of the fundamental laws of physics. They also provoke curiosity, driving scientists to explore the boundaries of known physics and search for new theories that can explain the behavior of the universe. Observational challenges. Dark energy, the mysterious force driving the acceleration of the universe's expansion, presents a formidable challenge to astronomers and cosmologists. The very nature of dark energy is elusive, making its observation and study an intricate puzzle. One of the primary observational challenges lies in the fact that dark energy does not emit, absorb, or reflect light, rendering it invisible to traditional telescopes. This invisibility forces scientists to rely on indirect methods to infer its presence and properties. For instance, the accelerated expansion of the universe, first observed through the study of distant supernovae, serves as a crucial piece of evidence for dark energy. However, this acceleration is subtle and requires precise measurements to detect, adding another layer of complexity to the observational process. Paradoxically, the more we learn about dark energy, the more questions arise. One such paradox is the cosmological constant problem. Theoretical calculations suggest that the energy density of the vacuum of space, which could be a form of dark energy, should be vastly higher than what is observed. This discrepancy between theoretical predictions and observational data has puzzled scientists for decades. Another intriguing paradox is the coincidence problem, which questions why the density of dark energy is comparable to the density of matter in the universe today. Given the vast differences in their evolution over time, this coincidence seems remarkably unlikely, sparking intense debate and speculation among researchers. To overcome these observational challenges, scientists employ a variety of innovative techniques and instruments. One such method involves studying the large-scale structure of the universe, such as the distribution of galaxies and galaxy clusters. By mapping these structures, astronomers can infer the influence of dark energy on the growth of cosmic structures over time. Additionally, the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, provides valuable insights into the early universe and the role of dark energy. Minute fluctuations in the CMB can reveal information about the universe's expansion rate and the nature of dark energy. However, these observations are incredibly delicate and require cutting-edge technology to detect and analyze. Despite these advancements, the enigmatic nature of dark energy continues to provoke curiosity and drive scientific inquiry. The observational challenges associated with dark energy highlight the need for continued innovation and collaboration in the field of cosmology. As new technologies and methods emerge, our understanding of dark energy and its role in the universe's acceleration will undoubtedly deepen, bringing us closer to unraveling one of the most profound mysteries of modern astrophysics: the cosmic microwave background. The cosmic microwave background, CMB, is the oldest light in the universe, a relic from a time just 380 years after the Big Bang. It's a snapshot of the universe when it was still in its infancy, and it's incredibly uniform, with tiny temperature fluctuations of about 1 part in 100. These fluctuations are crucial for understanding the universe's structure and evolution. They represent the seeds of the large-scale structures we see today, like galaxies and galaxy clusters. The CMB is also a key piece of evidence for the Big Bang theory and has been instrumental in shaping our understanding of the universe's composition and expansion. The CMB's uniformity presents a paradox. If we look at the universe today, it's incredibly lumpy, with galaxies, stars, and planets scattered throughout. But the CMB shows that the early universe was almost perfectly smooth. This seems contradictory. How did a uniform universe give rise to the complex structures we see today? The answer lies in those tiny temperature fluctuations. Slightly denser regions of the universe had a bit more gravity, pulling in more matter and eventually leading to the formation of stars and galaxies. It's a testament to how small differences can have enormous consequences over vast scales. Another intriguing aspect of the CMB is its role in understanding dark energy. The CMB provides a way to measure the universe's geometry and composition. By studying the patterns in the CMB, scientists can infer the amount of dark energy in the universe. Dark energy is the mysterious force driving the acceleration of the universe's expansion. The CMB's data suggests that dark energy makes up about 68% of the universe's energy density. This is a staggering figure, and it raises profound questions. What is dark energy? Why is it causing the universe to accelerate? These are some of the biggest mysteries in cosmology today. The CMB also helps address the horizon problem. This paradox arises because the CMB is uniform across the entire sky, even in regions that are so far apart that light hasn't had enough time to travel between them since the Big Bang. How can these regions have the same temperature if they've never been in causal contact? The solution to this paradox is inflation, a period of rapid expansion in the early universe. Inflation stretched the universe so quickly that regions that were once in contact were flung apart, explaining the uniformity of the CMB. This is a powerful example of how the CMB helps us understand the fundamental nature of the universe. Large-scale structure surveys. In the grand tapestry of the cosmos, the universe's expansion isn't just happening, it's accelerating. This mind-bending phenomenon is attributed to dark energy, a mysterious force that makes up about 68% of the universe's energy density. To understand this, scientists turn to large-scale structure surveys, which map the distribution of galaxies and galaxy clusters across vast cosmic distances. These surveys act like cosmic cartographers, charting the invisible hand of dark energy as it stretches space itself. One of the most intriguing paradoxes arises from the very nature of dark energy. It's a repulsive force that counteracts gravity, the very force that pulls matter together. Think of it like an invisible, cosmic rubber band stretching the universe apart. Yet, we can't see it, detect it directly, or fully understand its origins. Large-scale structure surveys help by providing a 3D map of the universe's scaffolding. By observing how galaxies cluster and spread out over billions of light years, scientists can infer the presence and influence of dark energy. It's like solving a cosmic puzzle where the pieces are galaxies, and the puzzle itself is the shape of the universe. These surveys aren't just about plotting points on a map. They involve intricate measurements of galaxy positions, shapes, and distances. For instance, the Sloan Digital Sky Survey, SDSS, has mapped millions of galaxies, revealing patterns and structures that hint at the underlying influence of dark energy. The Dark Energy Survey, DES, another ambitious project, uses a powerful camera to capture galaxy images and measure their redshifts, which indicate how fast they're moving away from us. This data helps scientists understand how dark energy has evolved over time and how it might shape the future of the universe. The paradox deepens when considering that dark energy's effects are only noticeable at the largest scales. On the scale of our solar system, or even our galaxy, gravity rules supreme. But zoom out far enough, and the universe's expansion becomes the dominant force. This dichotomy provokes curiosity. How can something so pervasive and powerful be so elusive? Large-scale structure surveys are our best tool for unraveling this mystery. They provide a window into the universe's past and a glimpse into its future, helping us understand the cosmic dance of dark energy and gravity. Future observations and experiments. The universe's accelerating expansion, driven by dark energy, remains one of the most profound mysteries in cosmology. To unravel this enigma, scientists are planning and conducting a series of future observations and experiments. These endeavors aim to precisely measure the universe's expansion rate, map its large-scale structure, and probe the nature of dark energy itself. One such initiative is the Dark Energy Spectroscopic Instrument, DESI, which will measure the redshifts of tens of millions of galaxies. By creating a 3D map of the universe, DESI hopes to shed light on the role of dark energy in shaping the cosmos. Paradoxically, the more we learn about dark energy, the more it seems to evade our understanding. For instance, the Hubble constant, which represents the rate of the universe's expansion, has been measured with increasing precision. Yet, different methods yield slightly different values, a discrepancy known as the Hubble tension. This inconsistency hints at potential new physics beyond our current models. Future observations, such as those by the Euclid spacecraft, will delve deeper into this tension, possibly revealing unexpected insights about dark energy's behavior. Another intriguing avenue of research involves studying the cosmic microwave background, CMB, the afterglow of the Big Bang. Experiments like the Simons Observatory and CMB-S4 will measure the CMB with unprecedented accuracy. These measurements can provide clues about the early universe's expansion and the influence of dark energy over cosmic time. Additionally, gravitational wave detectors, such as LIGO and Virgo, might one day detect signals from merging black holes or neutron stars at cosmological distances, offering another window into the universe's expansion history. The quest to understand dark energy is not just about answering fundamental questions. It's also about pushing the boundaries of technology and methodology. For example, the Nancy Grace Roman Space Telescope, set to launch in the near future, will conduct wide-field surveys to study dark energy through multiple complementary techniques. Meanwhile, ground-based observatories like the Large Synoptic Survey Telescope, LSST, will scan the sky, capturing vast amounts of data on galaxy clusters and supernovae. Each of these experiments brings us closer to unraveling the mystery of dark energy, but they also raise new questions, fueling the cycle of discovery and curiosity. Theoretical approaches. Dark energy is a mysterious force driving the accelerated expansion of the universe. To understand it, scientists have developed several theoretical approaches, each offering unique insights and raising intriguing paradoxes. One prominent theory is the cosmological constant, introduced by Albert Einstein as a modification to his field equations of general relativity. This constant represents a uniform energy density filling space, exerting a repulsive force that counteracts gravity. However, the cosmological constant comes with a significant paradox. The observed value of dark energy is incredibly small compared to theoretical predictions based on quantum field theory. This discrepancy, known as the cosmological constant problem, highlights a profound gap in our understanding of fundamental physics. Another theoretical approach involves quintessence, a dynamic form of dark energy that changes over time. Unlike the cosmological constant, quintessence is not a fixed property of space but a field that evolves, potentially explaining the accelerating expansion of the universe. This theory introduces the concept of a tracker solution, where the quintessence field adjusts to the changing conditions of the universe, maintaining a consistent ratio to the total energy density. Yet, quintessence also presents a paradox. It requires fine-tuning of initial conditions to match observed cosmic acceleration, raising questions about the naturalness of the solution. Despite this, quintessence offers a compelling alternative to the cosmological constant, as it allows for a time-varying dark energy density that could be tested through future observations. Modified gravity theories provide another avenue for explaining dark energy. These theories suggest that the accelerated expansion of the universe is not due to an exotic form of energy, but rather a breakdown of general relativity on cosmological scales. One such approach is the Dvali-Gabadadz-Paretai (DGP) model, which introduces an extra dimension to modify gravitational interactions at large scales. In this framework, the apparent acceleration of the universe could be a geometric effect rather than a manifestation of dark energy. However, modified gravity theories face their own set of paradoxes. For instance, they must carefully avoid conflicts with well-tested aspects of general relativity, such as the behavior of gravitational waves and the stability of planetary orbits. Additionally, these theories often introduce new degrees of freedom that can lead to unwanted consequences, such as ghost instabilities or violations of energy conditions. Theoretical approaches to dark energy also explore the possibility of a vacuum decay scenario, where the universe undergoes a phase transition to a lower energy state. In this context, dark energy could be a manifestation of a metastable vacuum, with the accelerated expansion representing the universe's evolution towards a more stable configuration. This idea is inspired by the concept of false vacuum decay in quantum field theory, where a metastable state can tunnel to a lower energy state through quantum fluctuations. However, this scenario raises a paradox. If the vacuum decay is a probabilistic event, why has it not already occurred, given the vast age of the universe? Moreover, the implications of such a phase transition for the future of the universe are profound and unsettling, as it could potentially lead to a Big Rip scenario, where the accelerated expansion tears apart all bound structures, including galaxies, stars, and even atoms. Quantum field theory and dark energy. Quantum field theory, QFT, is the theoretical framework that combines classical field theory, special relativity, and quantum mechanics. It's used in particle physics to construct physical models of subatomic particles. Dark energy, on the other hand, is a mysterious form of energy that permeates all of space and causes the expansion of the universe to accelerate. The connection between these two concepts is intriguing and has led to some fascinating paradoxes and theories. At the heart of QFT is the idea that the vacuum of space is not truly empty, but is filled with quantum fields that fluctuate and give rise to virtual particles. These fluctuations can have energy associated with them, known as vacuum energy or zero-point energy. When you calculate the expected amount of vacuum energy using QFT, you get a number that's about 120 orders of magnitude larger than the observed value of dark energy. This is one of the biggest discrepancies in all of physics, known as the vacuum catastrophe. It's like trying to measure the weight of a feather and getting a number closer to the weight of a blue whale instead. This paradox has left physicists scratching their heads and searching for new theories to explain the mismatch. One approach to reconciling QFT and dark energy is to consider that the vacuum energy we observe might not be the same as the vacuum energy predicted by QFT. Perhaps there's a mechanism that cancels out most of the vacuum energy, leaving only a small residual amount that we observe as dark energy. This idea is known as the cosmological constant problem, and it's one of the most pressing issues in modern physics. Another possibility is that dark energy is not a property of the vacuum at all, but is instead a dynamic quantity that changes over time. This would require a modification of our current understanding of QFT and could have profound implications for our understanding of the universe. The connection between QFT and dark energy is still an active area of research, and many open questions remain. For example, why is the observed value of dark energy so small compared to the predicted value? Is dark energy constant, or does it change over time? What is the fundamental nature of dark energy, and how does it fit into our understanding of the universe? These are just a few of the many questions that physicists are working to answer. The search for answers to these questions is not only important for our understanding of the universe, but also has the potential to revolutionize our understanding of physics itself. String theory and the landscape. In the vast cosmos, galaxies are not just drifting apart, they're accelerating away from each other. This acceleration is attributed to a mysterious force called dark energy, which constitutes about 68% of the universe's energy density. To understand this phenomenon, scientists have turned to string theory, a framework where the point-like particles of particle physics are replaced by one-dimensional objects called strings. These strings vibrate at different frequencies, giving rise to various particles and forces. String theory is a work in progress, with many unanswered questions and unresolved paradoxes. One of the most intriguing aspects is the landscape of possible universes it suggests. The landscape in string theory refers to the vast number of possible configurations the theory can take, each corresponding to a different universe with its own set of physical laws and constants. This concept is both fascinating and perplexing. It raises questions about why our universe has the specific properties it does. Why is the cosmological constant, which represents the energy density of space itself, so small? Why does it seem fine-tuned to allow for the existence of life? These questions touch on the anthropic principle, which suggests that our observations of the universe are biased by the fact that we, as observers, exist. The landscape of string theory provides a potential explanation for this fine-tuning, suggesting that our universe is just one of many in a vast multiverse, each with different properties. However, the landscape also presents challenges. It introduces a multitude of possible solutions, making it difficult to predict or explain the specific properties of our universe. This has led to debates about the scientific validity of the landscape and its role in explaining dark energy. Some scientists argue that the landscape is too vague and lacks predictive power, while others see it as a promising avenue for understanding the fundamental nature of the universe. The paradox lies in the tension between the richness of the landscape and the need for a more precise, testable theory. Despite these challenges, the landscape remains a compelling area of research, driving scientists to explore the deepest mysteries of the cosmos. Moreover, the landscape raises profound questions about the nature of reality. If our universe is just one of many, what does that mean for our understanding of existence? How do these other universes interact with ours, if at all? These questions push the boundaries of our current understanding and provoke curiosity about the fundamental nature of the universe. The search for answers continues, with scientists exploring new theories and conducting experiments to shed light on the enigmatic force driving the acceleration of the universe. The journey to understand dark energy and the landscape of string theory is far from over, but each step brings us closer to unraveling the deepest secrets of the cosmos. Anthropic principle and dark energy. Dark energy is a mysterious force that permeates the universe, causing its expansion to accelerate. One of the most intriguing aspects of this phenomenon is its connection to the anthropic principle, which suggests that the universe's properties are compatible with the existence of intelligent life. The anthropic principle comes in two flavors, the weak and the strong. The weak anthropic principle is a straightforward statistical argument. It posits that if there are many different universes with varying properties, we should only be surprised to find ourselves in one where conditions are just right for our existence. The strong anthropic principle, on the other hand, is more controversial. It suggests that the universe must have properties that allow for the existence of intelligent life, as if the universe is fine-tuned for our benefit. This idea is often invoked when discussing dark energy. The amount of dark energy in the universe is finely balanced. If it were too high, the universe would expand too quickly for galaxies and stars to form. If it were too low, the universe would collapse in on itself. The fact that dark energy is just right for life to exist is a striking coincidence, one that has led some scientists to invoke the anthropic principle. This fine-tuning raises a profound question. Is the universe's acceleration due to dark energy a mere coincidence, or is there a deeper explanation? One possibility is that dark energy is a property of space itself, a constant background energy that permeates the universe. This idea is known as the cosmological constant, first proposed by Albert Einstein. However, calculations of the cosmological constant based on quantum field theory suggest that its value should be vastly larger than what we observe. This discrepancy is one of the biggest unsolved problems in physics. Another possibility is that dark energy is a dynamic quantity, changing over time. This could explain why its value is just right for life to exist. However, we currently lack a theoretical framework to describe such a dynamic dark energy. The mystery deepens when we consider the multiverse hypothesis. If there are many universes with different properties, then it's not surprising that we find ourselves in one where dark energy is just right for life. But this idea is highly speculative and currently lacks empirical support. The anthropic principle and dark energy also raise questions about the nature of scientific explanation. Traditionally, scientists seek to explain phenomena in terms of underlying laws and mechanisms. But the anthropic principle seems to offer a different kind of explanation, one based on selection effects. If we are only able to exist in a universe with certain properties, then those properties are not surprising, even if they are highly improbable. This shift in explanatory strategy has led to heated debates among philosophers and scientists. Some argue that the anthropic principle is a legitimate scientific tool, while others see it as a last resort, to be invoked only when all else fails. The debate is far from settled, and it touches on deep questions about the nature of science and the limits of human knowledge. Meanwhile, dark energy continues to accelerate the universe's expansion, a silent and invisible force shaping the cosmos in ways we are only beginning to understand. Its connection to the anthropic principle adds another layer of mystery, one that challenges our intuitions and forces us to confront the limits of our understanding. So there we have it, folks. The universe, that vast and mysterious expanse, is not just expanding, it's accelerating, and dark energy is the enigmatic force behind it. We've explored how this mysterious energy makes up about 68% of the universe, yet we can't see it, can't detect it directly, and don't fully understand it. It's like having a neighbor who's always there but never shows their face, yet somehow influences everything around you. Think of it like this. Imagine you're in a car, steadily driving away from a landmark. Suddenly, you hit the gas, and the landmark starts disappearing from your rearview mirror faster and faster. That's what's happening with the universe. Galaxies are speeding away from each other at an ever-increasing rate, and dark energy is the unseen hand on the accelerator. But here's the paradox. If dark energy is causing the universe to expand faster, why isn't it tearing everything apart? Why are galaxies still held together by gravity? It's a cosmic balancing act, and scientists are still trying to figure out how it all works. This leaves us with more questions than answers. What exactly is dark energy? Is it a property of space itself, or is it something else entirely? Could there be other forces at play that we haven't discovered yet? The universe is full of mysteries, and dark energy is one of the biggest. So what can you do? Well, you can start by staying curious. The universe is out there, waiting to be explored and understood. And who knows, maybe one day, you'll be the one to unravel the secrets of dark energy. In the meantime, keep your eyes on the skies and your mind open to the possibilities. And if you're as fascinated by the mysteries of the universe as we are, stay tuned for our next video. We'll be diving into another cosmic conundrum that's sure to blow your mind. Until then, keep wondering, keep exploring, and keep looking up. The universe is waiting.